Astronomy Cast, episode 267 for Monday, May 28th, 2012, Infinities. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
I'm doing really well, and I think we want to remind people that they can celebrate the world not ending with us at the end of December.
Yes. So we are going on a cruise, departing out of Miami in the beginning part of December, second week of December, so hopefully kids will be most of the way out of school for Christmas break, and we're going to spend December 20th at Mayan ruins, stomping around, being archaeological fans, and celebrating the fact that the world is still around, and the Mayans built really awesome big things out of rocks.
Yeah, and so if you want to join us, you can go to astrosphere.org. There's a link right there on the homepage that sort of links you to information on the Not the End of the World cruise, and sort of information on how you can book a ticket on that. And then when you do book a ticket, make sure you say that Astronomy Cast sent me, and that way we'll be able to sort of gather you together into the special events that we're going to be doing just for Astronomy Cast. Fans.
There'll be live recordings. There's going to be all sorts of fun stuff. Yeah, we really hope that you'll be there, you'll join us, and we can all have a great holiday together.
Yeah, it's going to be a nice mixture of relaxation and astronomy, so I think this is going to be fun. So check it out. All right, let's get on with the show then. So forever is a funny thing. Today we're going to talk about infinities. That's right, all the different kinds of possible infinities, how you add them, subtract them, and use them to think about the scale of the universe. All right, Pamela. So you're just ready for some like killer first question, aren't you? Like, what would a 4-year-old ask? Why is So let's go back into the history of infinity. I mean, we're so used to this idea of infinity in about forever and about time going on forever, but infinity is actually, it's not really naturally occurring in science. So where did this concept even come from?
It's actually kind of awesome. Both infinity and zero are relatively new concepts in the grand scheme of the universe.
Infinity, I believe, but zero is a shocker.
Zero is the one that's always confusing. But so infinity is actually something that people didn't really think about, talk about, until somewhere between 400 and 500 years BC. And the idea is, as far as we know, lots of records have gotten lost throughout the centuries, millennia at this point. But the earliest account that we have comes from Zeno of Elea. And he basically was trying to come up with the idea of different paradoxes, different ways of breaking things up, and came across the idea that there were things that you had finite infinities, and we'll get to this, that you had potential infinities, and these were complicated ideas that left people kind of scratching their head, and eventually ended up leading to an entire branch of mathematics called set theory. And I'd like to state here, I have not taken set theory. I've taken calculus, I've taken relativity, pretty good at tensor math, have not taken set theory, so this is going to be a bit of a reach for me.
I've taken a little bit of set theory, but I wouldn't call myself a mathematician able to explain it. Right, okay, so I mean, this is a long time ago, and so someone made this leap to say, let's think about forever. Let's think about things that go on from now until forever, and that is something that just doesn't exist in nature.
Well, and also thinking about the numbers of things. In terms of you have a group of things, can you count them? Can you potentially count them? Are they uncountable? And this eventually led to, I don't know if it led directly because it was a different continent, but in India you had the way of looking at things where there were innumerable.
Innumerable?
Yes, beginning with the letter E things. And these are things that you can count. So you have a herd of sheep. You can count everything in the herd of sheep. It's a countable number. Then you have numbers that are uncountable, innumerable.
Innumerable?
Yes, that word. And these are things that are uncountable but are finite. So the number of hairs on my head, the number of grains of sand on a beach, these are finite numbers, but they're things that really you just can't count, not tractable. But then there's also things that are completely uncountable, and they're also not finite. So this is where the idea of how many pieces can you cut an apple up into, of what is the full expanse of a mathematical plane. And so here you start to get into things that have no boundary to them. They're unbound and uncountable, and that's where the concept of infinity started to come in.
Yeah, you could imagine someone saying, you know, I can count 1, 2, 3, 4, and I could do that forever. That I would never stop counting. I could just keep counting up, and there's got to be some way to describe that.
And that also starts to get on to, as people started to think more and more about the different types of infinity, the idea that there are countable infinite sets and uncountable infinite sets came up. So you now have, you're starting to talk about different types of infinities. So when I look at the set of whole numbers, 1, 2, 3, 4, 5, when I look at the set of even numbers, 2, 4, 6, 8, 10, well, both of those are infinite sets of numbers. But the 2, 4, 6, 8, 10 is smaller than the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Whoa, smaller? But they're both infinity.
You have different infinities. So the even numbers is a subset of all whole numbers, but they're both infinite, but you can start counting them and you're just never going to finish.
Oh, okay, so you could take, like, for example, you take your even numbers and you take your whole numbers and you just start to circle them, right? Take the 2 on the infinity, you take the 2 for the even numbers, and then you just match them up, and you end up with a whole bunch of the, I guess, of the integers of all the numbers that you're not matching up. All the odd numbers, essentially, you're not matching up. And so that essentially gives you a larger infinity. So you can actually have 2 different, or I guess an unlimited number of infinities of different sizes.
But because we know how the set progresses, 1, 2, 3, 4, 5, 6, 7, 2, 4, 6, 8, 10, these are called countable infinities. Now, at the same time, you can imagine that you take all the numbers between 1 and 2. So 1.1, 1.2, 1.20579, 12. And you just keep adding decimal points. Now you have the real numbers. 4/3, pi is a real number, e is a real number. And these numbers, with all of these decimal points added to them, you can create an infinite number of real numbers between 1 and 2. And then there's another infinite between 2 and 3. And then if you try and come up with a set of all the real numbers, that's an uncountable set. There's no way that I can sit here like I do with whole numbers and go 1, 2, 3, 4, 5. I can't do that with real numbers.
Right.
And so now you have an uncountable infinite set. So when you start looking at infinities, there's multiple types of infinities, and they're not all the same, and so this has led to entire branches of mathematics.
So where did the little infinity symbol come from? I'm making it in the camera.
Well, it's one of those things. To me, it's always looked like the number 8 fell over sideways and had a bad day. A lot of infinity signs are sort of an elongated number 8, and there's actually a little bit of arguing over exactly what the origins of it. John Wallis, who was a theologian, is credited in the mathematical literature with coming up with the symbols. This was in 1655 in De Sectionibus Conicus. Sorry, I can't pronounce Latin well. And it's argued over whether or not the symbol came from the numbers for 1000 in the Etruscan numeral set, where it was basically the letter C, a straight line, a backwards letter C. And if you smush all of that together, it kind of looks like a sideways number 8, sort of like the infinity symbol. There's others that say that it's a mutation of omega, which is the end of the Greek alphabet. So you have alpha is the beginning, omega is the end.
Mm-hmm.
If you take the lowercase omega, it's like a curly W. We'll curl that little W in on itself. Maybe you get the infinity symbol. So exactly what he used for inspiration is somewhat up for debate, but it was definitely John Willis that came up with the symbol that we now use.
And so, I mean, as we said, you can count to infinity, or I guess you can never count to infinity, but you can attempt to count to infinity. But infinity actually has a role to play. Mathematicians, physicists use infinity all the time in math to help with certain ideas.
So it really actually comes out left and right, and along with infinity you have to have the infinitesimal. So this is the idea that it's something so small that it's almost zero, but not really. And so you can have different sized infinitesimals, just like you can have different sized infinities, and it starts to get a little bit confusing to deal with at times. But you have to have both partner ideas. And this actually builds on what we were talking about last week when we talked about Archimedes. And Archimedes, when he was trying to figure out how to calculate the area under a curve, started with the idea that you take the curve and you divide it up into a bunch of sections that you can measure the area of, a bunch of small rectangles is what gets used when we teach it in modern mathematics classes. And by making the rectangles smaller and smaller, you can better approximate the area under the curve by summing all of these together. Well, if you bring in the idea of the infinitesimal, such that each rectangle is basically coming down to zero width, or at least as close to zero width as you can get, and then you're adding up all of these together by summing all of these infinitesimally small rectangles together, you have a continuum of rectangles that give you an accurate measurement of the area under the curve. And this was the idea that got us to integral calculus and differential calculus. And
those are used all the
everywhere.
Time by scientists.
Yeah, and so this dates back to Newton and Leibniz had to come up with calculus in order for us to have pretty much all of modern physics. So Leibniz was working on infinitesimals, Newton was working on physics. The two of them together both came up with differential and integral calculus, using it in somewhat different and overlapping applications. And with this idea that you can sum over various things, it allows you to start thinking in complicated ways. So you start summing functions from 0 to infinity, from negative infinity to positive infinity, to get what is the area under the curve, what is the rotation, what is the summation over a different set. There's lots of different applications where adding up all the little pieces starts to mean something.
Especially when you're able to slice up what you're looking at into, as you say, infinitesimally small pieces. So you're taking a set amount of information, but you're slicing it up so many times that you get an approximation, which is a very accurate mathematical estimate of this thing.
Right.
I know physicists use this process to estimate, in some cases, the force of certain like forces in physics and things like that.
Well, and the place that calculus most abruptly hits you over the head the first time is just looking at something as simple as velocity and acceleration, where you look at the changes in the shapes of the different curves of how far have you been displaced, what is your velocity over time, and you can use the derivatives of these different values to get to the next value, or to figure out how far you've gone if you do the integral to go backwards. And so the relationships between distance traveled, velocity, and acceleration all require the use of calculus to figure out changes over time and to figure out complete distances, complete velocities, and things like that.
So I think there's a great analogy that's been used about to sort of understand these different sizes of infinity. And we talked a bit about that, about how you could be matching up the evens and the odd numbers. And so there's the paradox of the hotel paradox. Have you heard this?
So this is Hilbert's paradox. This is a paradox that was discussed in the early part of the last century, where you can imagine that you have your normal hotel that has a finite number of guests. That's easy to deal with. Now, instead imagine that you have an infinity of new guests coming in. So you basically now have a countable infinity where one comes in, you put them in a room. Then you just keep adding rooms as you add guests. This is the same idea of there's a variety of different artwork trying to explain an infinite universe where you just keep taking an extra step or shooting an arrow, and where that arrow lands, well, you now just made the universe bigger. Well, in this case, you just add a guest, the hotel gets bigger. So this is still a countable infinity in the sense that it's a whole number of rooms, the same way we have integer numbers that are a countable set.
And the hotel is full.
And the hotel is always full because you're adding rooms for every guest. And so it's basically the set of whole numbers. Now, it starts to get a little bit yuckier when instead what you have coming up to the door is a whole series of coaches, and each coach now includes an infinite set of guests. So now I have a countable set of coaches, maybe. You can always say that there's an infinite number of driveways that each contain an infinite set of coaches. But now, because I have all of these coaches that each contain infinite guests, that's the same as the idea of there's an infinite set of numbers between 1 and 2 and an infinite set of numbers between 2 and 3 that are the real numbers. So this was a way of taking what to me seems perfectly natural, because I've been thinking about this part of set theory for a long time, but trying to make it sensible in a paradigm that many people have dealt with, which is the hotel syndrome. So you can imagine the mad construction workers on the roof of the building just adding rooms every time there's a new guest. It's a countable infinity. You can imagine the coach that has an infinite number of guests within it, and these coaches keep pulling up, and now that becomes uncountable.
Ugh.
Yeah, it hurts.
Yeah, but there's actually a great, I think it was on Horizon. If you do like a Google search on Infinity and Horizon, BBC Horizon. Yeah, there's a great whole episode just on Infinity, and they cover the hotel paradox in it quite nicely, and it's pretty great. So I highly recommend that. So I think where we need to sort of take this conversation now is to apply this into astronomy and cosmology. Right. You know, we've understood sort of what is this concept of infinity. How does this play out in astronomers' thinking of the sort of scale and size of the universe itself?
Well, the first place it really cropped up was with another paradox, in this case Olber's paradox. And Olber was a philosopher who went outside and basically looked up, and this is going to sound strange, but he realized the sky is dark and this is problematic. And again, this was happening in the last century. He actually worked on the paradox in the 1800s. And looking up and realizing the sky is dark had a couple of different consequences, because up until then, we kind of, as a society and our philosophy of thinking, had come to the conclusion that the universe is infinite in size, and if it's infinite in size, that means that every direction I look, no matter where I look in the sky, my path of my vision is going to end in a star. Now, if you start from the premise that the universe is also infinite in age, that means that the light from every single one of those stars has had time to reach us here on the planet Earth. And when we look into the sky, we should see, no matter where we look, the light of a star. And so the entire star should glow with the light of 1,000,000 billion suns. And we don't see that. And so this implied that our universe has to be either finite in size, finite in age, or finite in both. And this was a new way of looking at things where it was math, not religion, that was placing limits on the universe.
And but I know that sort of the way that ended up getting resolved was, I mean, partly, definitely the limited in age.
Yes, we do know the universe is limited in age. We're still working on going beyond that, is the crazy part.
Right. Well, and I guess that's the next step of this conversation. So, but I just, I think that's a fantastic sort of understanding of the universe for him to make, right? That
Yeah.
he looked around and said, why do I not see stars everywhere in the sky? Why is the whole sky not as bright as the surface of one gigantic star? Because
Right.
wherever you look, there should be photons streaming from stars. Even if they're infinitely far away, you're still going to get some stars. And it's really hard to wrap your mind around.
Though.
Yeah, no, absolutely. That is the implication of infinity. That if there is infinity, then there will be something everywhere. Right?
And it has to be infinity in both universe and time.
And in time. You break either one of those, and then you don't need to have the whole sky be a star.
And you can break both of them at the same time. So all he did basically was get rid of n of infinity, or all of them. And so that left a whole bunch of combinations for scientists to spend the next decades and decades working on figuring out.
Right, and so as you said, now thanks to Hubble, thanks to the cosmic microwave background radiation, we now are able to place a finite idea of the age itself of the universe at 13.7 billion years.
Yeah.
But the answer of whether or not the universe is finite or infinite is still an unknown.
Yeah, this is one of those things that really bothers us. So it was originally hoped that when we launched the Wilkinson microwave anisotropy probe, when we launched WMAP, that we'd be able to accurately measure the geometry of the universe. And it was also thought at the time that there was no acceleration value to how the universe is expanding. So we had this great vision in the mid-90s that we were almost there. We'd be able to figure out if the universe was infinite or not based strictly on a geometric argument. So if the universe contains a high enough density of material, then the light from that material will have a chance to travel all the way around the surface of the universe, where everything is gravitationally bound. Eventually the entire universe will have a giant crunch. So this was one of the fates of the universe. Then you also had the idea that you could also have a geometrically flat universe, which is the idea of an infinite Euclidean plane, except you're now thinking in 4 dimensions because you have time and the 3 normal spatial dimensions. And then there is also an open idea where if there wasn't enough mass, the universe would continue to the universe would continue to expand apart forever. Now, what we've discovered is we have a slightly more confusing situation. The universe has dark energy. This is an acceleration something, energy, force, pressure, and this dark energy is causing the universe to expand apart. Still doesn't rule out the idea of an infinite universe, just makes it a little bit harder to calculate. And looking at the data from the Wilkinson microwave anisotropy probe, WMAP, we're finding that the geometry is completely flat to within 0.5% of what we can measure. This adds up to could be infinite, probably infinite, but could also just be really, really, really big.
How big?
Well,
I guess what you're saying that is then because it's seen as flat,
yeah,
we're not seeing the curvature of it that would tell us that it is finite to a measurable level. We're saying it is definitely flat to the point that we can't tell if it's infinite or finite.
And the limits that we're putting on it are such that if the universe is infinite in size, the part of the universe that we live in is only a few % of the total universe. And when I say the part we live in, I mean the part that we can see, the part of the universe from which light has had time to travel since the Big Bang to the planet Earth, and we're able to observe it. And so when there's still the possibility that we're only seeing a fraction of the universe, all we're doing is putting limits on the size of the complete universe. And it's unclear if we'll ever actually be able to distinguish between an infinite and a finite universe. But there are potentials that if the universe is finite, we'll be able to measure it.
So would a better measurement of these differences in the cosmic microwave background radiation give us a more precise understanding of that minimum size of a finite universe?
It's not so much the better understanding of the geometry as with missions like the Planck mission, which is currently measuring the cosmic microwave background. There's the potential that we'll be able to see places where light from one place in the universe is being seen in two different places in the sky. And if we can find these places where essentially the universe has had a chance to wrap around itself, where the light has had a chance to wrap around itself and come at us from two different directions, perhaps that will, not perhaps, that will put limitations on how big the universe can be.
Whoa. So, hold on. So, this is crazy. So if you, in other words, if you are able to look at the cosmic microwave background radiation of the universe precisely enough,
yeah,
you should be able to see features mirrored in this microwave. You should look in one direction of the sky and see certain features, and then turn around and look at other features and see those same features on the other side of the sky, telling you that the universe is finite in size, and that if you go far enough in one direction, you will come back around from the other direction.
And one of the topographies that's preferred right now is the four-dimensional hypertoroid. So this is the idea that essentially we live on an expanding donut, and when you have a donut, the light on the donut is able to follow Euclidean geometry such that two rays of light always stay parallel to one another, and it can either wrap through the whole of the donut and the outside of the donut and come back to where it started, or it can race around the surface of the donut where you put the frosting down, and two rays will always stay parallel to each other no matter how you put them down on the surface of the donut. Now you can mathematically expand this to more different dimensions and maintain the idea of parallel rays, get the whole sucker expanding, and you can see how light from one of the sprinkles on the surface of the donut can come at one point from two different places in the sky.
So what are the implications then if we do live in an infinite universe? What does this mean for us as human beings here on Earth?
Well, I think we still live in such a small fraction of that universe that it really doesn't have any implications. But it does mean we can figure out the answers to questions. So you can say to the small child, yes, the universe is finite or infinite. It starts to bound our ideas for the Big Bang Theory. It just puts limitations on ideas.
No, but if it's infinite.
Well, if it's infinite, then it's still another different way to now solve an unbounded math equation. It's another way to look at the theories. But
I mean, there's mind-bending.
It's philosophical. It's a philosophical implication more than anything else, because now you're broken with the concept of the entire universe started out as an infinitely small point that exploded into existence, expanding all points at the same time, no center to this. And that was an infinite universe expanding from an infinitely small point. Not expanding from. That's still, there's no, we don't even have the language to say this.
So how do you, an
you go from
infinite
everything
expansion
infinitely compacted together to everything
infinitely large.
Yes. But infinite in all points.
Yeah.
And suddenly math hurts far more.
Yeah.
It's the same problem people have with relativity.
And it's worse than that, because then you have infinite numbers of. I mean, we've had this conversation about multiple dimensions, right? If you have an infinite universe, then anything that can exist will exist, and it will exist an infinite number of times. And so there will be an infinite number of sun-like stars out there, and around those infinite number of sun-like stars, there will be an infinite number of planets that kind of look like Earth, and in fact there will be an infinite number of planets that look exactly like Earth that happen to have evolved mammalian creatures, and some of which look like me and Pamela, and they will be recording an infinite number of Astronomy Cast episodes right now.
Now you add to this the problem of the potential for a multiverse, which is the idea that our universe may be one of many different universes that exist in perhaps a quantum foam, but perhaps branch off of one another. No matter how they come into existence, there's the potential for each of them to have different values for the different physical constants, so a different value of gravity, a different mass of the electron, a different fine structure constant. And so now you're looking at an infinite number of infinitely sized universes. Now this gets back to the whole real number problem, where there's an infinite number of numbers between 1 and 2 and an infinite number of numbers between 2 and 3. And so now what you have is infinite size within our universe, and there's an infinite number of universes, and it's turtles all the way down, but it's not. It's just math, and it hurts.
Right. Yeah, it's, there's a few very simple mathematical formula that would sort of wrap this all up into a nice tidy bow, but the philosophical implications are mind-bending. So then what about time? Is time infinite?
Well, so the way, unfortunately, that we have to deal with time within our universe is there was a t equals 0, and we can't go before t equals 0. So within the bounding box of the universe that we exist, time has a moment 0. Unless you go with some of the more complicated cosmologies that don't actually have a moment of Big Bang, that are more of expanding and contracting ideas. But for the majority of the cosmological ideas, you do have a t equals 0.
But then what about the other way?
Don't know.
Will you have a t equals infinity? I mean,
Well, currently, where our understanding is that we live in an accelerating apart universe, flat geometry or not, if the sucker's expanding apart, it's never going to come back together, so there's not going to be an end to the time. But then there's also ideas of perhaps there's going to be the chance that our universe and another universe touch and combine, and so that would essentially bring time in our universe to an end and start something new. So this is, think of two universes as soap bubbles that merge into one, or our universe could pop. And these are all terrible ideas, but they're not disallowed by physics.
Right, but I guess what I'm saying is that when you think about, let's say that that isn't the case, and that we're just going to deal with the situation that we have, which is this accelerating expansion of the universe, then
it's unbounded.
It is unbounded into the future. And then when you think about it, think about the absolute fortunate time that we happen to be here in this tiny fraction of the time when complicated life and energy and all these things were possible, because for the vast majority of the lifetime of the universe, it's just going to be a rapidly accelerating soup of particles.
Yeah, and
energy.
eventually, if protons do decay, it will eventually be a soup of nothing but energy. Nothing
but energy expanding, that you can never have any energy differential. There will never be anything else. There will be life. There'll never be, anything.
The future is bleak.
Television, yeah, and the fact that we live in this moment at the very beginning is quite cool. But then that's the the greater anthropic, lesser anthropic principle, right? Which is that we wouldn't be here to observe it if it wasn't possible. So, well, that was really cool, and I hope that everybody's minds have been sufficiently blown this week by the concept of infinity. It is super cool to think about this stuff. And I highly recommend, like I mentioned, search for this BBC Horizon documentary on infinity. It's great and covers a lot of these concepts.
And set theory is the thing to look at if you are into math and you want to understand more of this sort of thing.
Fantastic. Well, thank you very much, Pamela, and we will talk to you next week.
Sounds great, Fraser. Talk to you later. And now save.
Save. All right. $267.
Yes.
Cool. All right. Let me see if we've gathered any questions up. And like I said, I apologize. It's not as easy this time around because I don't have my super awesome comments tracker. Epileptic Zombie 360 wanted to know how these views of infinities affect the multiverse theory. So I guess you kind of covered that right at the end.
Yeah, we got to it at the end.
Right.
It hurts.
So I hope that's okay. Essentially, it just makes it more complicated. It takes infinity multiplied by infinity.
Yeah.
Ryan McIver wants to know how we can get our videos to work on a mobile device such as a tablet. It says unsupported video format. Any ideas?
You can use the YouTube.
So you can try watching this on YouTube Live, and see if that works differently than doing it in Google. I mean, in theory, what's happening is that we're now generating a live YouTube stream, and it's being embedded into Google Plus and on other websites as well. So you should be able to do that. Yeah, maybe try updating your version of Flash if it's on a tablet. I don't know if it'll even work.
Well, it depends on what device you have, because so last I checked, it worked on an iPhone if you looked at the YouTube stream.
So go to YouTube in the iPhone and see if you can watch. And it's on, right now it's on the Universe Today. On the Universe Today page, it's sort of like the top stream there, and you should be able to access it there.
Is it publicly listed?
Yeah, if you go to the Universe Today channel on YouTube, it is the first video, and it's actually should be showing live right now. Let's say Astronomy Cast episode 267, which is one of my uploaded videos. So, but yeah, I mean, I think the goal in the future is for this to all come together, so that you can watch these in all the different places, remember where you were, and it'll all be totally seamless. It's actually way better.
So I think you can see things the public can't see, because I don't see it listed on the Universe Today page.
Really?
Yeah.
So you go to the Universe Today on YouTube, and you go to my channel, Universe Today channel.
Yep.
I'm seeing a bunch of people that have commented on it.
Right, but I bet they got the link from Google+.
I don't think so. Here, I'm going to give you the link. If you go to, is it say youtube.com/user/Universe Today?
Well, slash Universe Today.
Yeah, /Universe Today, /user/Universe Today.
And so in the big thing is Astronomy Cast 266 Archimedes. In the featured playlist, I clicked on uploaded videos, and it's not listed there. So I'm pretty sure that it has a hidden URL that you can get via Google+, and in the future we probably need to make sure that we tweet the YouTube as well for people on mobile devices.
That is totally surprising to me. But anyway, we don't want to go into all this minutia. But if anybody's watching and kind of knows any more information, then that would be really cool. Okay, I'm going to log in, not signed in, and see if that has an impact.
Meanwhile, while he types.
Meanwhile, as I type, go ahead and answer something interesting.
Okay. Except I.
No, you're right.
YouTube. Yes. Thank you.
Oh no! I thought it was totally different. So I thought that it was live on YouTube at the same time that it was live. Well,
it is, but you have to get the YouTube link off of Google+.
Okay, so the people who are watching this on YouTube that are posting their comments over on YouTube, how on earth
from Google+.
Are you doing this? If you can put a comment in there, that would be very helpful, because that would be great.
So the way you do it is on Google+, when the video is playing, you click where it says YouTube,
and then it takes you to YouTube. I understand. Yeah, they should make that publicly available from the channel itself. Okay, I'm going to nag them about that, because that would be better.
Or just give us a toggle box, because I know a lot of the stuff that we're trying to get into Astrosphere vids, the fact that it doesn't start out public is better for our stats.
Yeah, okay. But some people are saying that they're seeing it on their YouTube video page. So if you subscribe to Universe Today on YouTube, this has got to be the most boring thing you guys have ever heard. If anyone has a question about infinity, about space and astronomy, feel free to post it into Google Plus or on YouTube if you somehow found your way there, or use the hashtag AstronomyCast, and we will be glad to answer it. Yeah. And we'll figure out our YouTube shenanigans later. Let me see if I got another question here. Yeah, I don't see any questions. I see people. Oh, okay. So Thad Sabo says a finite speed of light is necessary, which would have been...
Yes, a finite speed of light.
Right, and that's something that Olber would have known and considered. So if you had an infinite speed of light, then you wouldn't need a finite universe, right?
Yes.
Whoa. So that's actually the three pieces of the recipe, but one was known, and now two are known, which answers the paradox. Okay. Is there a name for an infinity of infinites?
I'm sure there is, but I have to admit my vocabulary for set theory doesn't get me to it. Sorry, this is where I have to say yes, but I have no idea what it's called.
Okay. So if anybody knows the name for an infinite infinity, an infinity of infinities, that would be helpful.
I think they're cardinal numbers, but I don't want to lie too badly.
Yeah. Okay. Well, you know what? I don't have any more questions. We clearly broke people's brains. So why don't we, while we've got people for a few more minutes, if anyone wants to recommend show ideas, we're more than happy to take some of your suggestions. Now we're 267 shows. We've recorded a lot of things, but if there's anything out there that anybody wants us to talk about in the future, just start posting some comments, and we'll cover them. What's my list right now? We've actually knocked off a bunch of them here. Let me see my current list. Mass, which is
energy.
Mass,
energy might be next.
Energy next, okay. And heat. So we actually have some really basic concepts that we haven't talked about yet. Animals in space, SpaceX, exploration of some of the other planets, making your own telescope, climate change. We did Archimedes, we did Eddington. The Chinese space exploration, or the Chinese Space Agency. Cool astronomy software that we recommend. The International Space Station. The Soviet space program, which we haven't even talked about. That's probably multiple episodes.
Yeah.
Abiogenesis, the Moon and Tides, Tycho Brahe. Someone recommended Saturn V and Werner von Braun. So lots of topic ideas, and whenever I sit down and actually brainstorm them, we come up with lots more. So if any of those sound really cool to you, then let us know. And if anyone has any other recommendations for topics, we can add them to our big list of ideas. Space Lab, the Swedish Space Agency. That's a good one.
There's so many little tiny space agencies.
Yeah.
Last summer I had the opportunity to attend the International Space University over in Graz, Austria as one of the instructors. And I was meeting early career individuals from the Romanian Space Agency, from the Russian Space Agency, from the Austrian Space Agency, from all these programs that we don't generally hear about because they tend to work more often cooperatively through the European Space Agency, but there are actually national programs as well.
Canadian Space Agency, hello.
Yes.
We have an arm.
You have an arm.
We have an arm. It's on the International Space Station. It's on the. It was on the space shuttle.
Don't you have two on the International Space Station?
Well, there's the. I don't think so. There's the Dexter system.
Okay.
Yeah, and it's sort of like a super duper crawling space arm that helps with the astronauts. So yeah. Peter, you asked a question. Oh, okay. Desislava Jeleva asks, Pamela, do you find compact topology theories for the universe more compelling, and why, if you do?
There's some things I choose not to have an opinion on, and that one starts to get so far out of my field of study that any opinions that I had would be based strictly on philosophy. So if I could design the universe, I would have finite universes and infinite numbers, but it's not my job to design the universe, and I don't do the math to solve the universe, so I leave real opinions to other people.
But can you explain even what a compact topology theory is?
It's the idea that you have closed surfaces. So you have a donut-shaped universe, you have a sphere-shaped universe. There's people who've gotten into crazy polygons of many, many scary sides, soccer ball-shaped universes, but such that the different flat parts of the soccer ball wrap around to each other. So there's all sorts of complicated closed geometries. But it's a lot of stuff that I have to admit, it's not parts of the literature that I'm fluent enough in to say more than a stomach-based opinion on.
Right. Okay, so Jafar101 asks on YouTube, if a 500-meter asteroid hits the moon, would that affect the Earth? That's a big asteroid.
It might.
Where.
It depends on what side, yeah. So it depends on where it hits. If the rebounded material got sent towards the planet Earth, that could have an effect, but the degree of the effect I'm unsure of. It might simply be meteor shower-sized effect.
Right, but definitely not knock the moon out of orbit and crash into the Earth or spin it away from the planet. You would need a much larger impact.
Yeah.
So keep going. But essentially, you keep going bigger and bigger and bigger. 10 kilometer, probably not. 100 kilometer, nah. 1,000-kilometer object?
Definitely.
Now we're cooking. Yeah. Now we're...
100-kilometer object with a high enough velocity could do something serious.
Yeah.
So you have to take into consideration both size and velocity, because the energy of the impact is mass times velocity squared. So you can have a small high-speed object that does just as much damage as a slow-moving larger object.
Yeah. Epileptic Zombie 360 wants to know about multiverse theory, and we've actually done a whole episode just on multiple universes. So if you go back through our archive, either on the Astronomy Cast site, you can go back and do a search for multiverse or multiple universes. We've done that.
Yes.
It was very interesting. And actually, there's a bit of overlap with what we're talking about here, because there's sort of multiple ways that you can get multiple universes. You can either have a multi-universe within the universe, this concept of infinity, or you can have actual multiple separate universes. Okay. So Jens is saying that I've actually got other questions in other locations. So I got to dig down some other locations to find other people's questions. So I will find those. Here we go. Mike Elher wants to know what are some of the astronomy software that we would cover on an episode about astronomy software?
I think it would probably turn into a multiple episode series where we did an episode on data reduction packages, so things that will allow you to get from raw images to either pretty or scientifically interesting images, probably both. And then observing planning software. So this is planetarium software, and then data mining software, so things like Worldwide Telescope that allow you to probe what are the data sets available, how do you explore the data sets that are available. And things
and then
like
consumer software. So we've got things like Stellarium and some of the cool iPad apps.
So there's lots of different things to do. We'll get to it before Christmas. But yeah, that's one that's going to require a great deal of research because the field changes so constantly.
Yeah. So it's definitely something we wanted to talk about. As you say, part of it is it changes. I mean, part of our goal is to provide episodes that can last forever, that you could pick up an episode of Astronomy Cast 10 years from now and listen to it, and it would still be as relevant as it was when we're recording it. Things like software, they change so often that we could mention a whole bunch of packages that nobody uses. Fortunately, astronomers are such fuddy-duddies that they stick with one piece of technical software written in COBOL and they just hang on to it for 10 years. So
I love the fact that in radio astronomy they're using the same software called APES that I used when I worked at Haystack Observatory in high school. So the same software has been used since I was a teenager.
That's exactly it, right. And so if there's any one thing, it's in scientific software, they tend to use the same software.
But it's not COBOL, it's Fortran.
Oh, Fortran, sorry, yeah, I know, the older Fortran. We learned Fortran in university when I went to university. That's how old it is. Have we done an episode about star colors? I think we have. Yeah, we did.
Yeah, we talked about it when we did the HR diagram.
Yeah. Arthur C. Clarke. That's a good idea.
He doesn't have a mission, does he?
He doesn't, I don't think, but he came up with so many ideas that were both relevant in science fiction, but also, I mean, he came up with the idea of geostationary satellites.
We should maybe do an episode or a set of episodes on ideas that first appeared in science fiction and then became reality. So will become reality.
I like that.
So bring up Clark's stuff, bring up Dyson's stuff. Not the vacuum Dyson, the other Dyson.
You mean the fact that Dyson spheres are now reality?
Well, they're not now a reality, but they have potential.
True. Yeah, no, Arthur C. Clarke would be great, though. Yeah, what a treat.
Gene Roddenberry? He's one of the only ones that came up with the iPad and a lot of the medical devices.
True. I like that. Cool.
I love how the new thermometers that they use in hospitals are IR devices, so they wave something over your forehead and your artery on your throat to get your temperature now. There's no sticking things in humans anymore.
So Delos Lava asks, how can we observationally determine if we live in an infinite universe?
We can't.
Right. I've read right now we can only put limits on how small the radius of a compact universe is. That's right. So there is no way to measure that you're in an infinite universe. You can only measure the lower boundary of its finiteness.
Yeah.
So you could say, I know that I live in a universe that is
n times bigger than what I can see.
Right. 100 billion light years across, at least. But it could be bigger and it could be infinite, but we know that it is at least 100 billion light years across. Or 100 trillion, or who knows what the number is.
Bigger than 100 billion.
Yeah. All right. Well, if anybody else has any questions, I'm going to take them. Otherwise, I will wrap this up, and then we will sort of move on to our next thing. So we're going to be recording our next thing, which is tomorrow morning, 10 o'clock, which is the Weekly Space Hangout.
Actually, that's not the next thing. The next thing is the Weekly Science Hour tonight with Emily Lakdawala. And that's at 6 p.m. Central, which is 4 p.m. Pacific. And then on the MyMoon Adobe Connect channel, all this information is on CosmoQuest. Go read our blog. Nicole, Noisy Astronomer, posted something. I'm giving a talk there at 7 on moon mappers. And then tomorrow, you're up.
That's right, yeah. Tomorrow then at 10, we've got the Weekly Space Hangout, where we give a rundown of all the big space news that happened this week, which is the exact opposite of Astronomy Cast.
Yes.
Which is why it exists, because people kept wanting us to put in news into Astronomy Cast, and we forbid it. But that's the way that we bring it in. Cool. Okay. And then we'll be doing another virtual star party on Sunday night, where we connect a bunch of telescopes live into a Google Hangout and take requests.
And we may or may not throw in additional surprise recordings of Astronomy Cast as we work to get ahead.
Yeah, trying to catch up and get ahead. So surprise. All right. Well, thanks a lot, Pamela, and thanks to everybody who was watching and listening. We will see all of you next time.
Bye-bye.
Bye.